And now we have João Novo on null and timelike circular orbits from effective 2D metrics.
So is the mic working? Can you hear me? Okay. So thank you for your presentation. So I am João. I'm a PhD student at Aveiro under the supervision of Pedro Cunha and Professor Carlos Herdeiro. First of all, I would like to thank the organizers for giving me the opportunity of presenting this work I developed a couple of years ago, which I think is very interesting and very different from some of the things that have been presented here. Okay, which concerns effective metrics. And I will first begin by saying what an effective metric is and why I think it is worth pursuing. Then I will use these effective metrics to study the light rings and the time-like circular orbits of generic spacetimes, both with and without black holes. So to the effective metric. So what is the motivation? So imagine that we have some very strange motion in our 4D spacetime manifold. And well, with an effective metric, we can map this geodesic motion to a motion on a two-dimensional surface, which is Riemannian. And well, this greatly simplifies the analysis because there's lots of literature on Riemannian manifolds and many known results, but this simplification comes at a cost because our original spacetime needs to have at least two Killing vector fields that are integrated out of the motion and allows us to get this effective 2D description. So for the purpose of this work, I will consider the very simple case of a spacetime that is both static, spherically symmetric, asymptotically flat, and four-dimensional, meaning that the most general line element that we can have is this one written on the board. And so we will further require that if this spacetime harbors a black hole, the black hole is non-extremal, and it is, if it harbors no black hole but a arrivalist compact object, it has to be regular, specifically at the origin, meaning that these metric functions must obey these expansions here. And now we will study the metrics of this spacetime. So we start with the Hamilton-Jacobi equation, which reads like this when we use the Killing vector field dt, and we focus on the equatorial plane because since we are considering spherically symmetric black holes, spacetimes, all motion is planar, so we can reduce to the equatorial plane. And we can rewrite this in this form, and we can see that a sort of 2D metric appears, which I called here alpha, and this alpha ij, which then contracts with the remaining momenta, which will be the radial and azimuthal momenta, is what I will call the Jacobi metric. And this describes a 2D Riemannian manifold. It is energy dependent, and its geodesics are the spatial projection of the spacetime geodesics. So now we can use this two-dimensional manifold to study the motion on a higher dimensional Lorentzian manifold, if we have these two Killing vector fields, at least. So this is very well known in the null limit. This has been used several times. Well, in the null limit, the energy is just a conformal factor, which we can then rescale this parameter, so we can set the energy to 1. And this has been used several times for gravitational lensing, for shadows, for analysis of the near horizon geometries, and even for analysis of light rings in double black hole solutions. So you have the references here if you want to pursue these directions further. And just to show you what I mean, I will consider the simplest example, that is the Schwarzschild spacetime. And this is the Schwarzschild metric, and when we do the dimensional reduction, we have this optical Schwarzschild metric. And we can see that, well, it will describe a surface of revolution, meaning that we can embed this two-dimensional surface on the 3D Euclidean space to see what really is going on. So this blue surface is the effective 2D manifold, and the effective metric is the induced metric on this manifold. And for example, here we can see the Schwarzschild light ring is just this constant radial coordinate curve, which, well, if you know a bit of Gauss's theorem and geometry of surfaces, you will see that this is a geodesics of this manifold because the normal vector to the curve is a normal vector to the surface. This was just an illustration to see what these sort of structures look like for a particular case. Now, I will tell you how we can study these surfaces with a crash course in differential geometry, and we will be considering both properties of the curves and of the surface itself. For the curves, we will require the geodesic curvature, which, well, you can see it's very similar to the geodesic equation, but then it is projected onto a vector that is normal to the manifold. So it will measure the failure of a curve to be a geodesic. So if we have a geodesic gamma, then its geodesic curvature must be 0. And since we are working with curves, well, the only relevant parameter is 1, which is the Gaussian curvature. There is no, well, the Riemann tensor and the Ricci tensor are all related to this Gaussian curvature, which is just a number, a scalar, and it is the product of the principal normal curvatures on the manifold. And this is important because, well, I give here two typical examples, the 2D sphere and the flat space. And, well, this is cutting a bit off the slide, but this is 1 over r squared, where r is the radius of the sphere. So the Gaussian curvature is positive all over the two sphere. And we can see that if we are at a point and draw two geodesics of the spacetime of the surface, then they will meet again. And if we are in flat space, then the geodesics will never meet again. And well, this is just some end wavy explanation, but this can be made rigorous. And well, if the Gaussian curvature of the surface is positive, then the geodesics that start nearby will eventually approach. And if it is negative, then they will continue to depart. So these are the two things we need to remember from this crash course on differential geometry. The geodesic curvature of geodesics vanishes, and the sign of the Gaussian curvature of the surface will determine the stability of this geodesic. So now we can apply this knowledge to the study of light rings, not to be confused with photon rings. Well, yes, Luciano?
Why do you talk about stability? I mean, normally we think about stability.
Okay, so this is a radial stability. So if we are in a stable orbit, you do a small perturbation, and if it comes back to the original orbit, then we say that the orbit is stable, and if the deviation just grows, then we say that it is unstable.
But in a previous example, you were saying K is positive, the geodesic will meet again.
Yes. So,
but then would you say that those are unstable geodesics?
No, it's stable, so they will meet again, so it's stable. So if you are in an orbit, a time-like circular orbit, for example, then you do a small perturbation, it will deviate, but then it will meet again. So we say that the orbit is stable. Yes, well, yeah. Well, yes, it's strange to talk about stability of a single geodesic. So think of stability of the potential, or for example, if we consider the potential for the motion of light in Schwarzschild, then the light ring will occur at a peak. So if we say that it is unstable because any small deviation from the peak will cause the light ring to, well, the light to disperse or to be absorbed from the black hole. So that's this sort of stability. So yes, I was getting into light rings, not to be confused with photon rings that we talked about yesterday. So the light rings are circular photon orbits. So, and they are a characteristic of the spacetime and not an observational feature as the photon rings. So the existence of the light ring implies that the geodesic curvature at a certain radius, because it will be a circular orbit, must vanish. And if we study the Gaussian curvature at the location of the light ring that is given by solving this equation, we obtain this expression here. So the sign of this geodesic curvature will determine the stability of the light ring. So if we plot this geodesic curvature for an arbitrary radius, at the roots of this function, we will have a light ring, and the slope at which it crosses the axis will determine its stability. And now we can use this information to determine how many light rings such a spacetime may have. If we consider the limits of the geodesic curvature, in the asymptotic limits we have the expected 1 over r behavior. And in the horizon limit, the geodesic curvature tends to the surface gravity of the black hole, which, since we are considering non-extremal black hole, this will always be negative. Oh, sorry, wrong direction. And if we are considering horizonless compact objects, then regularity at the origin means that the geodesic curvature will diverge at the origin. So for black rings, we will have geodesic curvature that have this sort of behavior. They will start at negative values and end at 0 from above. So we have to have at least one light ring, which is crossed with positive slope. So we'll have an unstable light ring. And additional light rings will always come in pairs, one additional stable light ring and one additional unstable light ring. So we'll always have one more unstable light ring than stable light rings, and the outermost one will always be unstable. This changes a bit in the case of compact objects, because now the geodesic curvature diverges at the origin and is positive at infinity. So we will always have an even number of light rings, and they will always come in pairs of stable and unstable light rings. This can give us some insight about the stability of the compact object, because it is expected that such stable light rings can lead to a buildup of energy that can trigger nonlinear stabilities and, well, make the compact object either collapse or disperse. And so, well, we have this condition for the number of light rings for compact objects. So now we will, yes?
What happens if the blue curve is only tangential to the 0 axis over there?
Well, you have sort of degenerate light ring that is radially stable from one direction and unstable from another. That is a very fine-tuned situation, but I think we can say that overall it would be unstable because it would be unstable towards one direction, if that makes sense. Yes?
Okay, so again, if you think about what I was presenting on Monday, in the case of a self-gravitating light ring, then the effective potential is flat, you say tangent, and it's tangent over a finite size. So if you stay away from the edges and you are inside that flat region, you are neutrally stable. You can have more small perturbation, you're not going to go and disperse.
Well, I should have said that for this we are considering mostly at least two smooth metric functions. I think that for the case you presented, the metric functions are not, the derivatives are not continuous, right? They are only C1.
You can have C infinity functions which vanish only on a given domain, and then they smoothly continue afterwards. It would be like bump functions. They're not analytic, but they're C infinity. But it would be a very weird example.
Perhaps an interesting example. Well, in that case, you'd have infinite light rings, right? So, which is strange to say the least. So, any more questions? So if not, Well, I will now move on to the study of time-like circular orbits, which are also relevant because either to MRIs or black hole accretion, it is important to know where such orbits can exist and where they cease to exist. And a major difference between time-like circular orbits and null geodesics is that, well, they typically exist over a range of the radial coordinates, so they will not exist isolated. However, what will exist isolated are orbits that separate the stability of these time-like circular orbits. So this sort of separating orbits will be the ones we will be interested in studying, and we call them marginally stable circular orbits. Okay, so these will have a constant radial coordinate because they are circular. They have vanishing geodesic curvature because they are orbits. And, well, since they are at the threshold of stability, the Gaussian curvature on the curve should vanish. So we can solve these two equations for the energy and the radius of these orbits. And solving the geodesic equation condition, we have this expression for the squared of the specific energy, so the energy per unit mass, which will give us the range where time-like circular orbits are possible. The numerator will always be positive outside an event horizon, and this factor here will vanish at the light rings. So the light rings will separate regions where we have positive energy or negative energy. So regions which with positive energies are those where time-like circular orbits are allowed, and those with negative energies are those where the time-like circular orbits are not allowed. And since the stability, since the stability of the light ring is determined by the slope with which it crosses the axis, we see that if we have a stable light ring, then radially above we have no time-like circular orbits, and radially below we have, and vice versa for the case of the unstable light rings. Now we can study the Gaussian curvature along these curves, and this can be decomposed in three factors. Well, the first is always positive outside a possible event horizon. The second one is precisely this factor that vanishes at the light rings, well, which is to be expected because it goes like 1 over the energy of square. So, and the third factor will vanish at the marginally stable circular orbit. So this will be the one that we are most interested in. But first we'll go have a closer look at the light rings and see that the derivative at the light ring of this quantity will always be negative. So there is always be an odd number of marginally stable circular orbits between light rings. Well, which is to be expected, right? Because if you have two light rings, then we will have, perhaps I should go back here. So imagine that this will be in sequence. So we'd have an unstable light ring, a region where time-like circular orbits are possible. Then we would continue until we reach a stable light ring. And then what we would see is that the radial stability of the time-like circular orbits would change from this location here to this location here. So we need to have at least one orbit that is at the threshold of radial stability. So now we consider both the asymptotic limit and the horizon limit. And in the asymptotic limit, we have the usual 1 over r behavior. And in the horizon limit for black holes, we have that this goes like the derivative of this GTT at the horizon. And this is always positive by construction. So this is the typical, typical behavior of the Gaussian curvature that indicates the structure of time-like circular orbits in the spacetime. This is, for example, for the Schwarzschild spacetime. We have an unstable light ring. Then we have no time-like circular orbits below these light rings. Then we have a region of time-like circular orbits. And then we reach sort of this Newtonian behavior of time-like circular orbits. And this is divided by the existence of a marginally stable circular orbit. But if we have a more exotic black hole that has more than one light ring, for example 3, we would have something like this. So at the light rings, the Gaussian curvature always crosses with negative slope. So we have the light rings here. This would be unstable. Then we have a region of unstable time-like circular orbits. Then a region of stable time-like circular orbits separated by the marginally stable. This case would be the true ISCO of the spacetime, the innermost stable circular orbit. And we would have a region where no time-like circular orbits are possible. And then this would repeat until we reach this Newtonian limit of time-like circular orbits. And well, such spacetimes are particularly interesting when considering accretion, for example, because you can have accretion here that, well, in the adiabatic limit will go from time-like circular orbit to time-like circular orbit until it reaches this marginally stable circular orbit, and then it would sort of plunge. So it's interesting to see if that plunge would only stop at the horizon or it would stop at this region where time-like circular orbits are possible. So this was the example for black holes. Now we can consider compact objects. The asymptotic limit is the same, but now the origin limit is different. It will depend on this coefficient F2, which is the quadratic coefficient of the expansion of the GDT. And this is related to the strong energy condition at the origin. So if F2 is greater than 0, then the strong energy condition is obeyed. If it's not, then it is violated. So we will have two different cases. The case where the strong energy condition is satisfied, such compact object would have stable time-like circular orbits all the way up to r equals 0 if it has no light rings. If it does, then we would have a similar structure to the case of the black holes. And otherwise, if the strong energy condition is violated, then the orbits near the origin would be unstable and we would have a marginally stable circular orbit. So the existence of such unstable time-like circular orbits can act as a probe for the violation of the strong energy condition in these compact object spacetimes. And well, I just want to say that although this is not evidently seen by this formalism, this is also true for stationary spacetimes that are rotating. So now, in a nutshell, what I said is that there are no time-like circular orbits between a stable and an unstable light ring, and there will always be an odd number of marginally stable circular orbits between an unstable light ring and a stable one, or infinity. And in the case of black holes, there are no time-like circular orbits between the horizon and the first light ring, which will be unstable, and they will always possess an odd number of marginally stable circular orbits between the outermost unstable light ring and infinity. And for horizonless compact objects, if they satisfy the strong energy condition, then we have stable time-like circular orbits near the origin, and if they violate, then the time-like circular orbits near the origin are unstable. And well, this summarizes the results I had to say today, but what I really want to remark is that these results are completely independent of the theory we are considering, and they are valid for any metric theory of gravity, because to reach these conclusions, we made no use of field equations, for example, or the energy momentum tensor that generates these solutions. So thank you for your attention.